Usually when we talk about computer memory, there is this underlying expectation of infinite capacity, like,
Yeah.
I don't know, a bottomless digital filing cabinet.
Right, yeah. The modern consumer experience is completely designed to hide the physical limitations of the hardware.
Exactly. You save a file, the hard drive spins, and the operating system just quietly confirms it. It is clean, it is out of sight.
And we operate under this comforting illusion that our machines will just, never truly run out of space to think.
Yeah, but the moment you step into the world of modern artificial intelligence, specifically these massive large language models that are handling complex ongoing conversations or like analyzing entire books, that illusion completely shatters.
Oh, absolutely. The bottomless filing cabinet is overflowing.
We are looking at a computational landscape where the sheer physical weight of the AI's short-term memory is basically choking the system. It has become an absolute bottleneck.
It is arguably the defining hardware crisis of modern AI development right now. I mean, the limitation isn't the AI's ability to process logic or quote-unquote think anymore.
Right, because the processors are astonishingly fast today.
Exactly. The processors are blazing fast. The problem is literally the physics of moving the memory around fast enough to keep those processors fed.
So it's a traffic jam.
Yeah, we are hitting a wall where the communication latency inside the chip itself dictates the speed of the AI.
Which brings us to the actual deep dive into the source material for today. We have a highly technical, incredibly dense research paper on the docket.
Brought to us by some really brilliant experts at Google Research, NYU, and Google DeepMind.
Yeah, it's titled TurboQuant-Online Vector Quantization with Near-optimal Distortion Rate. Now, I know vector quantization sounds like something that requires a chalkboard full of Greek letters to even begin to care about.
It is definitely a mouthful.
But the reality is, this abstract math is the hidden engine making the AI tools you use every single day faster, cheaper, and fundamentally smarter.
That is the core mission of this deep dive, to really unpack how this new algorithm TurboQuant manages to shrink these massive AI memory bottlenecks down to a fraction of their size.
And doing it without losing an ounce of quality, right?
Yeah.
Like actually hitting the absolute mathematical limits of data compression.
Yeah, the scope of what they have accomplished here touches on some of the deepest principles of information theory.
So to understand how scientists squish this data down and the brilliant mathematical tricks TurboQuant uses to do it in real time, we kind of have to look at the mechanics of how AI actually perceives and stores information first.
We need to start with the sheer weight of this memory. Like, why does an AI need to go on a diet in the first place?
Right, because it doesn't read English or Spanish or Python, it reads numbers.
Specifically, it reads high-dimensional vectors in Euclidean space.
Okay, let's break this down, because high-dimensional vectors in Euclidean space sounds incredibly intimidating.
It really does.
If I remember my high school geometry, a two-dimensional vector is just a point on a piece of graph paper, right? Like an X and a Y coordinate.
Yep, that maps perfectly.
And a three-dimensional vector just adds depth. So an X, a Y, and a Z.
Right, a vector is simply a list of numbers representing coordinates. But in deep learning models and vector databases, the information is stored as a list of numbers that can be thousands of dimensions long.
Thousands.
Thousands. If an AI is looking at a word, or a concept, or even a pixel in an image, it isn't just using 3 coordinates.
Wow.
The paper mentions standard embeddings, like the OpenAI 3 embeddings, and those operate in 1536-dimensional space, or sometimes even 3072-dimensional space.
So instead of just X, Y, and Z, we have this massive alphabet of coordinates going all the way up to 1536 just to pinpoint a single concept.
Exactly.
But why does a single word need thousands of dimensions? Like, what are those numbers actually representing in the real world?
Well, they represent semantic nuance. Imagine you were trying to map the concept of a king.
Okay, a king.
One dimension might capture the concept of royalty. Another dimension captures gender. Another captures historical context. And another might capture power dynamics.
So every subtle shade of meaning gets its own axis.
Yes. By utilizing thousands of dimensions, the AI can plot the exact semantic location of king relative to queen or president or pawn.
That is fascinating.
The AI captures the subtle relationships between literally every piece of human knowledge by giving them distinct coordinate values in this massive spatial architecture.
Okay, that makes the sheer scale of the data much more tangible for me. And I guess here is where the memory wall hits.
Right.
Because when you are interacting with a chatbot using a decoder-based transformer model, which is the underlying architecture for almost all modern LLMs, The AI generates text, one token at a time.
Yeah, a token is roughly equivalent to a word or a piece of a word. You watch it stream across the screen.
But for the AI to ensure the very next word it generates makes logical sense, it has to maintain context, right?
Absolutely. It needs to remember everything it just generated and everything you, the user, prompted it with.
And it does this by storing those vectors, those massive 1,536-dimensional lists of numbers from all previously generated tokens.
Yes, and this specific storage arena is called the KV cache, which stands for key value cache.
So the KV cache is effectively the AI's short-term working memory for that isolated conversation.
That's a perfect way to put it. The architecture of the transformer demands it.
Why does it demand it so rigidly, though?
Well, every time a new token is generated, the AI calculates what we call a query and compares it against all the historical keys in the cache. It has to figure out which passwords are most relevant to what it should say next.
Got it. And then it retrieves the corresponding values.
Exactly. Now, if the context length is short, say you're just asking for a quick recipe, the KV cache is small.
Right, no big deal.
But as these models become more capable, the context lengths are growing exponentially. We're asking them to analyze entire 300-page legal documents or huge code bases containing tens of thousands of lines of code.
Which means the AI is suddenly forced to store tens of thousands of 1,536-dimensional vectors in its active short-term memory all at once.
All at once. And the physical hardware simply cannot accommodate that kind of throughput.
So this latency in AI generation, like the lag you experience when ChatGPT pauses, that is overwhelmingly a communication bottleneck.
It really is. The data is stored in the HBM, which is the high bandwidth memory, but the actual math is performed in the SRAM, the super fast memory sitting right next to the processing cores on the GPU accelerators.
The processing cores are incredibly fast, but they are just constantly waiting for the HBM to send them the massive vectors.
They're starved for data.
It feels like comparing the KV cache to a stenographer in a courtroom.
Oh, I like that analogy.
Right. Like on day one of a trial, the stenographer has a small stack of notepads. If the judge asks what the witness said an hour ago, it's easy to reach back and check.
Very quick retrieval.
But as the trial drags on for months, which represents our massive context length, the stack of notepads gets so incredibly high that just reaching back to find a quote from the first week takes forever.
The judge is waiting. The lawyers are waiting.
Exactly. The actual thinking hasn't stopped, but the physical retrieval of the memory brings the entire court to a halt.
Yeah, the bottleneck is the physical act of fetching the notepads. And the thing is, the AI isn't merely retrieving the quote, it is mathematically analyzing those past vectors against the current one.
How so?
It is calculating inner products and measuring Euclidean distances.
Break down the inner product for me. I mean, why is that specific calculation so vital to the AI's functioning?
So the inner product is basically the mathematical mechanism the AI uses to determine similarity.
Okay.
When the AI generates a new query vector, it needs to know which key vectors in the cache are semantically related to it. It computes the inner product, which roughly translates to checking if two vectors are pointing in the exact same direction in that 1536-dimensional space.
Like checking if they align.
Yes. If the inner product yields a high value, the concepts are highly related, and the AI pays attention to that specific memory. But if the vectors are enormous, pulling them from the HBM to calculate that inner product creates catastrophic latency.
And this issue isn't isolated to chatbots either, right? The source text explicitly highlights this as a critical failure point for vector databases as well.
Oh, definitely. Vector databases are the backbone of retrieval augmented generation, or ARA.
Right, RAG. We see that everywhere now.
When you ask an enterprise AI to, say, summarize the Q3 earnings report, the system doesn't actually have that report memorized in its core training data.
Because it's proprietary or brand new.
Exactly. Instead, it turns your query into a high-dimensional vector and executes a nearest neighbor search across a massive database of corporate documents.
So it is looking for the vectors in the database that sit closest to the query vector in that Euclidean space.
Yes. And searching through billions of high-dimensional vectors to find the nearest neighbor is incredibly computationally expensive.
The problem is undeniable. The AI is carrying around too much weight, the stenographer's stack of notes is too tall, the HBM can't feed the SRAM fast enough.
It's a fundamental physical limit.
My immediate layperson instinct is to just squish it. you know, compress the data. We use files all the time on our computers. If we shrink the vectors, the memory bottleneck disappears.
That is the logical next step, yes.
But I assume if we just blindly compress the AI's memory, we risk the AI hallucinating or forgetting crucial details. How do we shrink the data without destroying the mathematical meaning of the inner product?
And there it is. This is the core dilemma of the entire field. The industry refers to this as the quantization conundrum.
The quantization conundrum.
Catchy. You are chasing speed, but accuracy is absolutely non-negotiable. If you compress a vector sloppily, the resulting inner product calculations become wildly inaccurate.
Give me an example of what happens when it goes wrong.
Well, the AI might calculate that the vector for cat is pointing in the same direction as the vector for bulldozer. The attention mechanism misfires completely, and the model begins to hallucinate total nonsense.
So how has the industry historically approached this compression to try and avoid that?
The foundational approach is called vector quantization, or VQ. And the lineage of this concept actually traces all the way back to Claude Shannon's source coding theory, which was developed in the late 1940s and 1950s.
Claude Shannon, the father of information theory.
The very same. His work established the absolute physical limits of digital communication. He basically defined the mathematical boundaries of how much you can compress a signal before the original information is irrevocably lost.
That's wild that we're still building on his theories from the 40s.
It's foundational. Vector quantization is the practical application of trying to reach those limits. It is the process of taking floating point coordinate values and converting them into low bit width integers.
Let me stop you there. I want to make sure the mechanics of that are totally clear. What is the actual difference between a floating point value and a low bit width integer in terms of memory weight?
Good question. A floating point value is the standard way computers handle highly precise decimals. Think of a coordinate value like 0.14159265 stretching out with high precision.
Lots of decimal places.
Right. To store just one of those numbers, the computer typically dedicates 16 or 32 bits of memory.
Okay.
Now multiply that by 1,536 dimensions and then by tens of thousands of tokens. It is an enormous amount of data. A low bit width integer, on the other hand, is tiny. It restricts the value to a very small set of whole numbers, using only 1, 2, or maybe 4 bits.
I see. You are taking a highly specific, sprawling decimal and literally snapping it to the nearest simple whole number. You are massively shrinking the footprint.
You are. But the consequence of snapping that highly precise decimal to a simple integer is the loss of detail. Information is destroyed.
Right, because you rounded it.
Exactly. In Shannon's terms, you introduce distortion. And in the context of this specific research paper, they measure that distortion as mean squared error, or MSE.
Okay, so the objective of vector quantization is to shrink the data down to these tiny bit widths while keeping that mean squared error, the distortion, as close to absolute zero as theoretically possible. Now, the historical context here in the paper is fascinating. They mentioned researchers like Zador in 1963 and Gershow in 1979 advancing this theory. People have been trying to solve this since the 1960s.
Yes, the mathematical framework was there, but early vector quantization was purely theoretical because it was paralyzingly expensive from a computational standpoint.
How so?
To find the optimal way to quantize a multidimensional vector, the algorithms had to perform brute force nearest neighbor searches across all possible combinations of quantization points. Computers in the 1970s simply couldn't execute that math in any practical time frame.
Which brings us to the modern era, where we have GPU accelerators capable of processing trillions of operations per second.
Right.
But according to the research, even with modern hardware, we are still trapped in this brutal trade-off between two flawed methodologies, offline methods and online methods.
Let's examine the offline methods first. They're often referred to as data-dependent methods. The most prominent example is product quantization, or PQ, alongside various Hessian-based methods.
What's the fundamental flaw with them?
These approaches rely on heavy preprocessing. Before they can compress anything, they must ingest the entire dataset, analyze the distribution of all the vectors, and build a highly customized codebook.
How does that codebook actually get built? Like, what is the algorithm doing during that pre-processing phase?
It typically uses clustering algorithms, like k-means.
Okay.
Imagine taking millions of vectors and plotting them in high-dimensional space. The algorithm looks for natural clusters or groupings in the data. It calculates the center point of each cluster, which we call the centroid.
The center of the cluster. Got it.
The codebook is essentially a lookup table of these optimal centroids. When it's time to compress a vector, the algorithm finds the nearest centroid and simply stores the ID of that centroid rather than the massive vector itself.
Oh, okay. So instead of storing the exact coordinates of my house, I just tell the computer,
Yeah.
I live in cluster number 7. And cluster number 7 is just the general neighborhood. That saves an immense amount of space. And because the algorithm studied the whole city beforehand to find the best neighborhoods, the distortion is minimized.
That's a great analogy. It is highly effective for static data sets. If you have a massive database of images that never changes, offline methods are excellent.
But I'm guessing they're terrible for something dynamic.
They are catastrophic for streaming AI generation, which is exactly what the KV cache requires.
Because in an active conversation with a chatbot, the dataset doesn't exist yet.
Right. The AI is literally inventing the data token by token.
You can't pause the conversation, gather up all the future words, run a heavy k-means clustering algorithm for an hour to build a custom dictionary, and then resume the chat.
You cannot build a data-dependent codebook on data that hasn't been generated yet. This operational reality forces us toward online methods.
Online meaning on the fly.
Yes. Online or data-oblivious methods do not require a pre-computed codebook based on the specific dataset. They apply a fixed compression algorithm instantly to whatever data is streaming into the system.
Honestly, that sounds like exactly what we need. Why isn't online quantization the undisputed champion here?
Because without that custom-tailored codebook, online methods historically suffer from atrocious distortion rates. They are flying blind. They blindly snap values to a fixed grid, and the mean squared error skyrockets. The accuracy degrades so much that the AI begins to fail.
That makes sense.
Furthermore, the researchers point out a structural issue. When engineers have tried to design online methods that retain accuracy, they often end up with architectures that are completely incompatible with modern GPU hardware.
The paper specifically cites a recent grid-based product quantization alternative that manages to avoid preprocessing, but fails spectacularly in real-world application because it's agonizingly slow on GPUs. Why does a modern GPU struggle with it?
It comes down to vectorization. A GPU is fundamentally different from the CPU in a laptop. A CPU is like a few highly intelligent workers who can do very complex tasks quickly. A GPU is like a massive factory floor with thousands of specialized, smaller workers.
Okay.
They aren't as smart individually, but they can execute thousands of simple calculations simultaneously. That is parallel processing.
Right.
But if an algorithm requires sequential steps where worker B cannot begin their calculation until worker A finishes theirs, the entire factory floor grinds to a halt.
Because they're all waiting on each other.
Exactly. The thousands of workers sit idle waiting for a sequential bottleneck to clear. That grid-based method has sequential dependencies, making it absolutely useless for the real-time demands of AI.
I need to understand why this is so difficult fundamentally. If compression is, at its core, just taking a large, highly precise decimal and rounding it to a smaller integer, why does online quantization automatically entail sacrificing so much accuracy?
It's a fair question.
If I'm just taking a number and snapping it to a smaller number on a fixed grid, why is that process inherently sloppy just because it's happening on the fly?
The underlying reason is the geometry of high-dimensional space. The coordinates inside a 1536-dimensional vector are not beautifully isolated, independent numbers.
They aren't.
No, they interact. They correlate in incredibly messy, unpredictable ways. A change in one coordinate can drastically alter the semantic trajectory of the entire vector relative to the other 1,535 dimensions.
Oh, I see.
You aren't just rounding a single number in a vacuum, you are altering a complex geometric shape. Blindly snapping numbers to a grid without understanding the localized structure of that specific dataset destroys the delicate geometry.
And when that geometry is destroyed, the inner product calculations, the AI's ability to measure similarity, completely fall apart.
That's it, exactly.
So the interconnected, messy geometry of the data is the core obstacle, which sets the stage perfectly for TurboQuant's first major innovation.
The researchers needed a way to tame that chaotic geometry on the fly without needing to analyze the whole dataset first.
They needed to eliminate the messy correlations. And this is the foundation of stage one, the MSE-optimized TurboQuant.
Yes, and the breakthrough they engineered relies on a technique called random rotation.
Okay, this was the moment in the paper where the counterintuitive nature of the math really stood out to me. Before TurboQuant even attempts to compress or quantize the data, it takes the incoming high-dimensional vector and multiplies it by a random rotation matrix.
It is a stunningly elegant application of statistics. Imagine the vector as a line pointing in a highly specific, complex direction across 1,536 dimensions. TurboQuant takes that vector and subjects it to a random, multidimensional spin.
I have to ask for a breakdown of the logic here. The AI has spent massive computational energy calculating the exact, precise location of this semantics vector, right?
Right.
It knows exactly where the concept belongs. Why would you deliberately take that pristine data and randomly scramble its orientation before trying to save it? That sounds like shaking a filing cabinet to organize the folders.
It seems entirely paradoxical until we examine the statistical phenomena that occur in high-dimensional spheres. The researchers leveraged a consequence of the central limit theorem.
The central limit theorem.
Yes. When you randomly rotate a vector in a sufficiently high-dimensional space, an extraordinary smoothing effect takes hold. Every single coordinate within that rotated vector begins to follow a highly predictable statistical pattern known as a beta distribution.
A beta distribution. What does that actually look like conceptually?
Well, in the context of thousands of dimensions, this beta distribution converges rapidly into a standard normal distribution, a classic bell curve.
Oh, okay.
Suddenly, the wild, unpredictable geometry of the data just vanishes. Every single coordinate, regardless of what semantic nuance it originally represented, now looks like a neat, predictable bell curve centered around zero.
And the paper emphasizes that through this rotation, the distinct coordinates become almost completely independent of each other.
Yes, and independence is the critical unlock here.
Yeah.
In statistics, when variables are independent, the value of one variable gives you absolutely no information about the value of another. Because the coordinates no longer interact or correlate in those messy, intertwined ways, TurboQuant is free from the burden of analyzing the entire 1536-dimensional geometry simultaneously.
It doesn't need to find complex clusters in hyperspace.
Exactly. It can look at each individual dimension, each coordinate, in complete isolation.
I want to try an analogy to visualize what this random rotation achieves. Let's say I am trying to pack a chaotic, oddly shaped collection of items into a suitcase.
Okay, a suitcase.
I have shoes, a hairdryer, a stack of books, and several ceramic coffee mugs. Trying to compress this, squishing it into a smaller box, is a nightmare because the items correlate differently. The hairdryer doesn't fit next to the shoe, the mug blocks the book.
The geometry is heavily intertwined.
Exactly. That is our standard high-dimensional vector. So applying random rotation is like taking that entire messy suitcase and tossing it into a massive industrial centrifuge.
A centrifuge, I love it.
You spin it at blinding speeds, exerting such immense forces that all the items break down into perfectly uniform grains of sand.
And the sand represents the beta distribution.
Right. Now, the grains of sand are entirely independent of each other. I no longer have to worry about how the complex shape of a hairdryer fits against a ceramic mug. I can just scoop the independent sand into identical little square boxes without any wasted space.
The centrifuge metaphor captures the exact mechanical benefit perfectly. By pulverizing the complex geometric correlations into independent, uniformly distributed sand, TurboQuant shifts the problem from a massively complex vector quantization problem to a vastly simpler one, scalar quantization.
Wait, what is the distinction between vector and scalar quantization here?
Vector quantization attempts to compress the entire multidimensional point all at once. Scalar quantization compresses a single one-dimensional number.
Oh, I see.
Because the coordinates are now independent, TurboQuant can deploy an optimal one-dimensional scalar quantizer on each coordinate individually. To do this, it utilizes the Lloyd-Max algorithm.
Yeah, I noticed the Lloyd-Max algorithm mentioned frequently in the methodology. How does it optimally compress a single coordinate?
The Lloyd-Max algorithm solves a continuous one-dimensional k-means problem. Knowing that the data now perfectly matches a bell curve, the algorithm calculates the exact, mathematically optimal way to place boundaries along that curve to minimize the mean squared error.
How does it place those boundaries?
It basically divides the curve into buckets. Values near the peak of the bell curve get smaller, tighter buckets because the data is denser there. Values on the long tails get wider buckets.
And because the researchers know exactly what the beta distribution looks like, they don't even have to run the Lloyd-Max algorithm on the fly.
Exactly the opposite. Because the distribution is universally predictable after the rotation, they pre-compute the optimal Lloyd-Max buckets for various bit widths, like 1 bit, 2 bits, 3 bits long before the AI ever runs.
Wow.
They bake these optimal codebooks directly into the system.
So when the actual data streams in during a live chatbot conversation, the computational overhead is almost zero.
The execution is instantaneous. The vector arrives, TurboQuant applies the random rotation matrix, the coordinates transform into independent variables, and the algorithm instantly snaps each coordinate to the nearest precomputed centroid in the Lloyd-Max buckets.
That is wild.
It is a completely online, data-oblivious method that achieves near-optimal mean squared error. And crucially, because every coordinate is processed identically and independently, the algorithm is perfectly vectorized.
The GPU parallel processing factory floors can execute it flawlessly without a single bottleneck.
Yes, all the tiny workers are busy.
It is an incredibly elegant piece of engineering. We have a compression engine that requires zero pre-processing, runs at blinding speeds on modern GPUs, and achieves mathematically optimal mean squared error compression. It seems like the quantization conundrum has been completely solved. We could just deploy this into the KV cache and be done.
It certainly appeared that way at first. But when the researchers actually analyze the downstream effects of this compression specifically, what happens when the AI tries to search that data later? They uncovered a hidden, fatal mathematical flaw.
Okay, so we're moving into the bias trap. The paper reveals that while they successfully optimized the mean squared error, the inner product calculations were silently breaking down.
Yes. The entire purpose of the KV cache is to allow the AI to calculate those inner products to find similar vectors. The paper proves mathematically that if you utilize a purely MSE-optimized quantizer, especially at extreme compression levels like a 1-bit width, your inner product estimations become heavily biased.
I really need to understand this bias. The paper notes a massive multiplicative bias at 1-bit widths. Specifically, the inner product is off by a factor of roughly 2 divided by pi.
Right.
Why does optimizing for mean squared error inherently skew the inner product?
The underlying math reveals a conflict between minimizing distance and preserving magnitude. Mean squared error is entirely focused on keeping the compressed point as physically close to the original point as possible in space.
Right.
But at 1-bit compression, you only have 2 choices for a coordinate, a positive value or a negative value. When you snap the complex data to just 2 points to minimize the average distance error, you systematically shrink the mathematical magnitude of the vectors.
So the vectors are fundamentally shorter.
Yes. And the inner product calculation relies heavily on magnitude. Because all the compressed vectors are artificially shortened, the resulting inner product calculation systematically underreports the similarity.
So the AI might pull the wrong memories from the KV cache because the similarity scores are uniformly suppressed by that 2 over pi factor.
Exactly. As you allocate more bits, like 3 or 4 bits, this bias naturally shrinks because the magnitude is preserved better.
But the entire objective is to operate at 1 or 2 bits to solve the memory crisis.
Precisely. At those low bit widths, the bias completely ruins the retrieval accuracy.
The elegant centrifuge trick inadvertently created a structural blind spot.
It did.
To fix it, the researchers engineered a 2-stage algorithm. This is where the paper moves from clever to somewhat mind-bending. Stage 1 is the MSE TurboQuant we just discussed. But the methodology dictates that you deliberately starve the algorithm of 1 bit.
You intentionally restrict its resources. If your overall budget for compression is 3 bits per coordinate, you only allow stage 1 to utilize 2 bits.
Okay.
You run the Lloyd-Max scalar quantization using only 2 bits to capture the macro structure of the data. It achieves an excellent mean squared error, getting you 95% of the way there, but it leaves behind a mathematical error, a residual.
So wait, the residual is the exact mathematical difference between the original uncompressed vector and our slightly compressed 2-bit version. It is the literal measure of the mistake.
Exactly. It is the leftover variance. Stage 2 targets that residual. You take the leftover error and you apply a completely different mathematical transform to it using your final reserved 3rd bit.
Which is the quantized Johnson-Lindenstrauss transform.
Yes.
The QJL transform. I need you to slow down and walk me through this because the logic feels utterly backwards here.
It does seem counterintuitive.
You were telling me that I should take my pristine data, deliberately compress it slightly worse than my budget allows, and then use my final bit of memory to compress the mistakes of the first compression.
Right.
How does that mathematically fix a massive multiplicative bias in the inner product? It sounds like trying to fix a leaning tower by measuring how much it leans and then building a tiny, equally crooked tower right next to it.
It is a phenomenal question, and the answer lies in understanding what the quantized Johnson-Linden-Strauss transform actually does. The Johnson-Linden-Strauss lemma is a foundational concept in geometry.
What does limit state?
It states that you can project high-dimensional points down into a much lower dimensional space while largely preserving the distances between those points.
Okay.
The researchers use a quantized version of this. They take the residual error, multiply it by a random projection matrix, and then quantize the result to a single bit, just a +1 or a -1.
A +1 or a -1 based on a random projection. How does that help?
Because the QJL transform is mathematically proven to be a perfectly unbiased statistical estimator for inner products. Let's think of it in terms of polling.
Polling, okay.
Stage 1, the MSE compression, is like doing a massive nationwide census. It gets the bulk of the demographic data highly accurate, but the methodology introduces a systematic bias, say. It constantly undercounts rural areas by 10%.
So this census gives us the macro structure, but it is fundamentally flawed.
Precisely. Stage 2, the QJL transform, isn't just another census. It is like sending out a highly specialized team of statisticians to execute a randomized, perfectly unbiased sample of only the rural areas that were missed.
I see.
The QJL transform doesn't care about minimizing the physical distance of the error. It acts as a statistical counterbalance. By using that final bit to apply QJL to the residual error, you are adding an unbiased corrector back into the equation.
So the MSE stage captures the massive shape of the data, minimizing the spatial distance, while the QJL stage injects a mathematically pure statistical correction to fix the magnitude problem.
The synthesis of the two is absolutely remarkable. The combination of the MSE baseline and the QJL correction yields near-optimal distance error rates, but with absolutely zero bias for the inner product estimation. The AI can calculate similarity perfectly, even at extreme low-bit compression.
That is a brilliant two-stage architecture. And the crazy thing is, the researchers weren't satisfied with merely building an engine that performed well empirically. They ventured into the realm of pure information theory to prove mathematically that it's nearly impossible for anyone to ever build anything significantly better.
This is a critical component of the paper, hitting the absolute limits of information. We return to Claude Shannon and his source coding theory, specifically looking at the Shannon lower bound.
Break down the Shannon lower bound for me. Like, what does it truly mean to hit the absolute limit of information?
Information theory establishes that there is an immutable physical limit to how much data can be compressed before the signal is permanently destroyed. It is a fundamental law in the universe, akin to the speed of light or absolute zero in thermodynamics.
Wow.
The Shannon lower bound dictates the absolute minimum distortion, the lowest possible mean squared error that can be achieved for a given bit rate. If an algorithm attempts to compress the data past the Shannon lower bound, the information is gone.
Period.
Period. No future technology, no quantum computer can ever recover it.
It is a hard mathematical floor. And the researchers set out to prove how close TurboQuant gets to that floor. The methodology they use for this proof involves Yao's minimax principle. This is another dense concept. How does game theory play into proving a compression algorithm?
Yao's minimax principle is a powerful tool in computational complexity. In simplified terms, it is a way to establish the absolute worst-case performance guarantee of an algorithm.
Okay, walk me through that.
It relates the performance of the best possible randomized algorithm dealing with worst-case inputs to the performance of a deterministic algorithm dealing with maximally difficult randomized inputs.
So they're basically pitting the ultimate defensive algorithm against an adversarial ultimate offensive dataset to see where the unbreakable baseline lies.
That's a great way to summarize it. By running TurboQuant through the gauntlet of Yao's minimax principle, they generated a rigorous mathematical proof establishing that TurboQuant's distortion rate is bounded.
Bounded by what?
They proved that it operates within a tiny constant factor of the absolute information theoretic lower bound.
How small of a factor are we talking about here?
Across any bit width configuration, the distortion is within a factor of roughly 2.7 from the absolute limit of physics. And when operating at a 1-bit with the most aggressive compression, it is only 1.45 away from absolute perfection.
To put that into perspective, it's like the researchers didn't just build a really fast sports car. They calculated the absolute physical limit of how fast any theoretical vehicle could ever travel in our atmosphere without disintegrating.
Right.
And then mathematically proved that their car is running at 99% of that physical limit.
The magnitude of the achievement cannot be overstated here. They solved the online quantization problem so thoroughly that any future algorithm developed by any other lab can only ever improve upon the efficiency by fractional margins. They have effectively scraped the bottom of the Shannon lower bound.
That theoretical proof is staggering. But, you know, theory and wind tunnel mathematics are one thing. The real question is how this hyper-optimized engine performs when you drop it into the messy, chaotic environment of a massive large language model. How does it handle the semantic nuances of actual language and sprawling vector databases?
The empirical validation is just as robust as the theoretical proof. The paper details a gauntlet of industry-standard benchmarks. Let's look at the classic needle-in-a-haystack test first.
I have always appreciated the literal naming of the needle in a haystack test. How exactly is it structured in this context?
Researchers hide a single, highly specific sentence, the needle, at a random location deep inside a massive, sprawling document. The haystack.
Okay.
In this specific experiment, the haystack was up to 104,000 tokens long.
104,000 tokens. That is the equivalent of stuffing a random serial number into the middle of a dense 300-page novel and asking the AI to retrieve it accurately based on a single prompt.
Exactly. They executed this test using the Llama 3.18b instruct model. They deployed TurboQuant and compared it against several state-of-the-art memory compression methods, specifically SnapKV, PyramidKV, and KV-Cat.
And how hard did they squeeze the memory?
They enforced a stringent memory compression ratio of 0.25. This means the AI is only permitted to utilize 25% of its normal KV cache memory, a 4x compression factor.
So the AI has a quarter of its usual short-term memory to process an entire 300-page novel. What happened to the competing algorithms?
As the context length grew towards the 104,000 token limit, the alternative methods began to fail catastrophically.
Really? How so?
Methods like SnapKV and PyramidKV rely heavily on token dropping. They try to guess which tokens are unimportant and simply discard them to save space. They struggled with recall.
Oh, wow.
The AI literally started forgetting where the needle was because the algorithms had deemed the surrounding context or the needle itself unworthy of saving.
The stenographer just started throwing away notepads to save space and inevitably threw away the critical testimony.
Exactly.
How did TurboQuant handle the 104K limit?
TurboQuant achieved the exact same performance curve as an uncompressed, full-precision baseline model. Operating at a quarter of the memory footprint, it performed as if the memory hadn't been touched at all.
Wait, really?
Yes, it retrieved the needle perfectly every single time across the entire context window.
A 4x memory reduction with zero degradation in recall performance. That alone is a massive operational victory. But the paper also details the long bench test, which evaluates real-world tasks rather than just finding hidden sentences.
Long bench comprises complex tasks, single and multi-document question answering, summarization of large texts, and complex code completion tasks. To maximize performance here, the researchers utilized non-integer bit precisions.
Non-integer bit precisions.
They configured TurboQuant to operate at 2.5 bits or 3.5 bits per channel.
I have to pause you there, because the concept of a half-bit defies basic computer science to me. A bit is a binary state. It is a 1 or a 0. You cannot have 2.5 bits. How is the algorithm achieving a fractional bit precision? Are they segregating the data and giving some numbers VIP treatment while compressing the rest harder?
The mechanism you just described is exactly what they built. It is a highly sophisticated strategy known as outlier splitting. In the internal activations of any large language model, the data is not entirely uniform. There are always a handful of values that are wildly different from the rest, massive mathematical outliers. Research has proven that these outliers are structurally critical to the LLM's logic and attention mechanism.
So if you mess with the outlier...
If you aggressively compress an outlier, the model's reasoning collapses and it hallucinates.
So you cannot subject the outliers to the same aggressive compression as the normal data.
Exactly. So TurboQuant analyzes the channels and splits them into two distinct groups. It identifies the 32 weirdest, most mathematically extreme numbers, the outliers, and allocates them a luxurious 3 bits of precision.
Okay, 3 bits for the VIPs.
Then it takes the remaining 96 normal numbers and compresses them aggressively down to 2 bits.
They're running 2 independent parallel instances of TurboQuant simultaneously. One tuned for high fidelity, one tuned for maximum compression.
And when you average the memory footprint of those 3-bit outliers and the 2-bit normal values across the entire vector, the effective average precision mathematically equates to 2.5 bits.
That is so smart.
By protecting the outliers, TurboQuant consistently outperformed all baselines across the QA, summarization, and coding tasks on the Longbench suite, even at that minuscule 2.5-bit effective footprint.
It is a remarkable piece of dynamic engineering. Now, shifting focus slightly, we discussed earlier how this isn't just about chatbots. The KV cache is one problem, but massive vector databases driving enterprise RH systems face similar bottlenecks. How did TurboQuant perform in the database retrieval experiments?
The empirical results in the vector database domain were arguably even more dominant. The researchers tested TurboQuant against standard product quantization PQ and a newer, highly regarded method called RapidQ.
Okay.
They tested them on massive complex datasets, including DBpedia and the 1536-dimensional OpenAI 3 embeddings. The primary metric here is recall at top depth.
Which measures what exactly?
It measures how consistently the algorithm places the mathematically true nearest neighbor within its top search results.
So it measures whether the database actually returns the correct document when you query it. How did the recall compare?
TurboQuant established a clear superiority in recall accuracy. But the truly mind-bending metric, the one that fundamentally alters the landscape of how these databases can be built, was the indexing time.
This goes back to the difference between offline and online methods. Offline methods like PQ have to build the code book first.
The paper includes Table 2, which documents the quantization time required to compress the massive 1536-dimensional dataset down to 4 bits. Standard product quantization, which requires running co-means clustering over the dataset to build the centroids, took roughly 239 seconds to index.
239 seconds, so a few minutes.
The newer RabbitQ method took an agonizing 2,267 seconds.
So 167 seconds. That is nearly 38 minutes just to prepare the data before you can even begin searching it.
And TurboQuant's indexing time for the exact same massive dataset, 0.00013 seconds.
0.00013 seconds. That is effectively zero. It is instantaneous.
It is the operational definition of zero. That time delta represents the difference between a real-time, fluid streaming AI system that can ingest a document and converse with you seamlessly, and a system that requires you to wait half an hour for a database to compile its code books.
Wow.
TurboQuant provides superior recall, it mathematically guarantees perfectly unbiased inner products, and it executes the entire process in 0.0013 seconds.
It's time to take a step back and really synthesize the journey we've just been on. We started by examining the crushing memory wall that is suffocating modern AI models, the massive ever-expanding KV cache of high-dimensional vectors that clogs the physical hardware pathways between HBM and SRAM.
We explored the historical quantization conundrum where engineers were forced to choose between the slow offline accuracy of product quantization or the fast, mathematically sloppy online methods.
Right, and then we unpacked the breakthrough mechanics of Stage 1, the MSE-optimized TurboQuant. By utilizing random rotation, the algorithm acts as a multi-dimensional centrifuge, transforming messy, correlated vectors into perfectly predictable, independent beta distributions.
Allowing for instantaneous scalar quantization via the Lloyd-Max algorithm.
But that created the bias trap, ruining the inner product calculations at low bit widths. We looked at the elegant two-stage fix, where the algorithm deliberately sacrifices a bit during the MSE stage, only to deploy a Quanti's Johnson-Linden-Strauss transform on the residual error.
This brilliantly injects a perfectly unbiased statistical correction into the equation, completely fixing the inner product magnitude.
We explore the theoretical depths of Yao's minimax principle and the Shannon lower bound, proving that this algorithm is pushing right up against the absolute limits of physical data compression.
And finally, we saw the empirical validation. 4x compression with zero performance loss on 100K token documents, fractional bit precision through outlier splitting, and indexing times of 0.0013 seconds compared to 38 minutes for legacy competitors.
It represents a rare synthesis of profound theoretical information mathematics and hyper-practical hardware-aware software engineering.
It really is a landmark paper.
Which brings us back to the ultimate question. Why does this dense, highly technical mathematical paper matter to you, the listener?
Yeah, why should you care?
It matters because this is not merely back-end trivia for server farm administrators. This algorithm and the foundational principles it proves is the exact reason the AI on your mobile phone or the proprietary RG database your company uses can ingest a 300-page PDF and answer your questions instantly.
Without requiring a liquid-cooled supercomputer the size of a warehouse just to maintain its short-term memory.
It fundamentally democratizes access to massive AI context windows. By shrinking the memory footprint so drastically while preserving perfect accuracy, we can deploy smarter, infinitely more context-aware models on vastly smaller, cheaper, and more energy-efficient consumer hardware.
But the very success of this paper leaves us with a truly provocative final thought to mull over. We established today that algorithms like TurboQuant are already scraping the absolute Shannon-defined limits of data compression physics.
They have hit the mathematical floor.
So what happens when AI models inevitably keep growing? What happens when consumer demand pushes context windows from 100,000 tokens to 100 million tokens?
And we literally cannot compress the underlying vectors any further because the laws of information theory forbid it.
Right.
When the filing cabinet can't be compressed anymore, are we going to need entirely new optical or quantum hardware paradigms?
Or will we have to fundamentally rethink the architecture of how an artificial intelligence remembers information in the first place?
When you reach the limits of physics, you can no longer optimize. You must invent. That is the next great frontier for AI research.
And we will be here to dive into it when they publish the next paper.
Thank you for joining us on this deep dive into the source material.